On the left side, I have two capacitors connected in parallel, C1 and C2. I want to replace these two capacitors with one equivalent capacitor that I'm calling C sub EQ. Let's presume that initially all the capacitors have no charge, and I'm going to add some charge. I'm going to add 1 coulomb, and I will develop a voltage V. On the equivalent capacitor, I'm going to do the same. I'm going to add 1 coulomb of charge and develop a voltage V. Since the capacitors are equivalent, the voltages will be the same. Now, when I add the charge to the left side, the charge, some of it will go on to C1 and some of it will go on to C2. The larger capacitor will consume most of the charge. So let's see if we can derive an equation for the equivalent capacitor. Now recall that the charge on a capacitor Q is equal to the capacitance times the voltage across the capacitor. So the charge on C1 I can write as C1 V. The charge on capacitor C2 I can write as C2 times V. The same voltage appears across C1 and C2. For the equivalent capacitor, I can say C EQ times voltage is equal to the charge on CQ. So the charge on C1 plus the charge on C2 is equal to the equivalent charge on CEQ. Now notice that the V's cancel. I'm left with a very simple equation. CEQ equals the sum of the parallel capacitors, C1 plus C2. So for capacitors connected in parallel, to get the equivalent capacitor, you just add the two together. Let me erase this. Now let's do the same thing for series capacitors. On the top I have C1 and C2 connected in series. I'm going to inject a current of 1 amp into the left side for 1 second. And below I have an equivalent capacitor that replaces C1 and C2 with one capacitor called CEQ. And again, I'm going to inject 1 amp for 1 second into CEQ. Since they are equivalent, I will get a voltage V at this terminal and the same voltage V on the capacitor at the bottom. Now note that as I inject this 1 amp for 1 second, I get current flow into C1 and out of C1 into C2 and out of C2 into ground. So the same current flows in C1 and C2. So the same charge accumulates on C1 and C2, which I'll call Q, and Q on C2. The same thing happens to C equivalent down below. I run 1 amp for 1 second and I develop a charge on CEQ. So all the capacitors receive the same charge. So let's see if we can derive an equation for the equivalent capacitor to C1 and C2. Now let's recall that charge is equal to the capacitance times the voltage across the capacitor. So the voltage across C2 I'll call V2, and the voltage across C1 I will call V1. So the total voltage is the sum of V2 and V1. So the V is equal to V1 plus V2. We can solve the top equation for voltage. If we do that, we get voltage is equal to Q divided by capacitance. So let's replace V in this equation for the CEQ. So in that case, I have the voltage is charge divided by CEQ, and that's equal to the V1, which I can write as Q divided by C1 plus the voltage V2 that I can write as Q divided by C2. Now notice that the charges all cancel out, and let's scroll down a little bit, and I'm left with 1 over CEQ is equal to 1 over C1 plus 1 over C2. I can solve this for CEQ. CEQ equals 1 divided by 1 over C1 plus 1 over C2. Now I can multiply the numerator and the denominator by the same value, and it won't change the equation. So let's multiply the numerator by C1 times C2, and do the same thing for the denominator, C1 times C2, and I get C equivalent is equal to C1 times C2. C1 will cancel. I'll be left with C2 plus C1. So the answer for the equivalent capacitor is the product of the two capacitors divided by the sum of the two capacitors. Very similar to the equation